Hello all. In the previous video, we have seen the refraction from rarer to denser at convex spherical refracting surface. Now we are going to see refraction from denser to rarer medium at a convex spherical refracting surface. So this is denser medium, this is convex spherical refracting surface, this is rarer medium having refractive indices same mu1, mu2 for rarer and denser medium respectively. So the first thing is we show the refracting surface, this is convex. Then we draw a principal axis passing through the center, this is pole. So then we are going to draw the normal to this surface. The normal intersects the principal axis at center of curvature C. PC is the radius of curvature. Okay, now here it is from denser to rarer. So the object is in the denser medium O. So the ray goes from O. It meets this surface XPY. Show the arrow at the point A. Now it gets refracted. That is denser to rarer. So it will bend away from normal. There is another ray coming from point O which will pass undeviated, that is along the principal axis, and these two rays intersect at a point which is the image I. Now again we are going to mark the angles. Okay, this angle is alpha with the object, with the image is beta, with the center of curvature it's gamma. Once you understand the basic things in this refraction at spherical refracting surfaces, okay, all others like we did previously, okay, after we mark this angles alpha, beta and gamma, we use exterior angle property. Yes, and now we are going to also have to mark the angle of incidence. This is angle of incidence I. This is angle of refraction R. Please draw this R and gamma carefully. You should not get confused. Now in triangle IAC, we are going to use exterior angle property. So see the angle IAC. Here we can use R equals to lambda. R is equals to beta, R is equal to beta plus gamma. Equation 1. Now we are going to consider another triangle OAC. And similarly using exterior angle property, see the triangle OAC, we can write gamma is equal to I plus alpha. Therefore, I is equal to gamma minus alpha, equation 2. The next thing is we have to use the Snell's law. Now using Snell's law, here it is very important thing. The ray is going from denser to rarer. Now the general formula Snell's law is sin I by sin R is mu 2 1. Because the ray is passing from 1 to 2. But here it is passing from 2 to 1. Okay, for all the details, please watch the very first video of the ray optics, where we have discussed, okay, how we write the formula of refractive index. So here if I say sin I by sin R, okay, now the ray is coming from this medium 2 to 1. So it will be mu 1, that is a refractive index of 1 because it is entering into the medium 1 with respect to 2. So it is mu 1 with respect to 2, which is equal to mu 1 by mu 2. Then as I and R very small angles, okay, we can approximate sin I to be equal to I and sin R is approximately equal to R. So we have the formula psi by r equals to mu1 by mu2. This is very main point in this derivation denser to rarer. If you make mistake here writing mu2 1, okay, your entire derivation will go wrong and will get a wrong formula. So now we have I and R. I by R is mu1 by mu2. Then we are going to substitute this I and R here. First we'll cross multiply. So mu2 I equals to mu1 R. That is mu2 gamma minus alpha is equal to mu1 beta plus gamma. This is our equation 3. Now once you get this, what we are going to do is, please see the angles alpha, beta, gamma. Now we are going to drop one perpendicular from A, which will intersect the principal axis at M. Now we'll consider the triangles, okay, AOM, ACM, AIM, so that we get this angles alpha, beta, gamma in this triangles. And as the angles are very small, here we have written that sin I and sin R are equal to I and R. Similarly, even tan of the angles is equal to the angle. So here I can find tan alpha and consider it to be alpha and then substitute in this. So tan alpha is nothing but alpha, which is equal to, if you see this triangle OAM, so alpha will be AM by MO. Similarly, beta will be AM by MI and gamma is equal to AM by MC. Now we have alpha, beta, gamma, which we are going to substitute here in the equation 3. Also note this from the ray diagram. This distance is PO is the object distance U, PC is radius of curvature, PI is the image distance V. We have to measure all the distances from the pole. And we are going to consider pole like an origin, and all the distances to the right side are positive, to the left side are negative. So substitute. You can take AM common and cancel that out. So we get this. You can see in the numerator there is AM term. In each term it is AM, so we can cancel it. Now you can see that P and M are very close. Okay, so MC is going to be considered approximately equal to PC. MO will be PO, MI will be PI. So as M and P are close, MC will be equal to PC, and PC, if you see, it is nothing but the radius of curvature, but to the left side, so it is negative minus R. PO, MO is approximately equal to PO, and PO is object distance, that to the left side, so it is minus U, and MI nothing but PI, which is plus V, image distance, but to the right side, so plus. So please understand the correct sign convention. Right side of the pole, like positive x-axis, distances are positive. To the left side, the distances are negative. Now we are going to substitute this all. MC is PC is minus R. This is MO. So MC is PC is minus R. MO is PO is minus U. MI is PI is plus V. And MCs are in minus R. Now once you substitute all this, you open the bracket. I'm going to take the r term that side. So we have mu2 by u plus mu1 by minus v or minus mu1 by v is equal to mu2 by r minus mu1 by r. Just shifted the r term to the right side. Then we are going to get a final formula. See the difference, rarer to denser and denser to rarer.